Okay, in the previous video, I introduced you this idea of slicing with planes parallel to the xy plane, xz plane, or yz plane. And that's the same as these planes are all given by equations like x equals a constant, or z equals a constant, or y equals a constant. And when you take a surface given by the equation, say x squared plus y squared minus z squared equals 5, or anything involving x, y, and z, and you plug in that value for the variable, then the equation you get, according to this principle here, that looking at the intersection of a surface with a plane, comes out to just plugging in that value for that variable. Then that gives you what the intersection looks like, and you'll be able to kind of piece together what it should look like. Just a quick review of what we did. Previous video, let's look at a new example in this video. This is called a paraboloid, and it's given by the equation of the form x squared plus y squared equals z. So if you didn't know what this graph looked like, if we didn't know that it looked like this kind of parabola that's been spun around the y-axis, then how could we figure out that that's what it should look like? Well, the idea is, so I'm going to erase this as if we didn't know what it looked like, and I'm going to just look at this equation, x squared plus y squared equals z. I want to start by looking at these kind of horizontal slices. Remember that these are given by z equal to a constant. And I'm going to just try different values for that constant and see what the intersection of that plane would be with this mystery surface. Now, for instance, if I put z equal to -1, or indeed anything negative, what you'll notice is that we have the equation. You'd plug that in here, and you'd say x squared plus y squared equals -1. But x squared plus y squared has to be positive, or at its lowest, it's 0. It can never possibly be negative. So it doesn't intersect the z equal -1 plane at all. So whatever this shape is, it has this minimum, it has this bottom, and it can't be negative. So these z equal -1 planes, or all these negative planes, will never touch my surface. Okay, the surface misses them. What about my z equal to 0 plane, the xy plane itself? What about that? Well, if you plug in z equals 0 here, x squared plus y squared equals 0. But the only way that's possible is if both x and y are 0. So xy has to be the origin. In other words, it has to be a single point. Okay, what about, so that's the case when z equals 0. So now we know what its intersection is with the xy plane is. Great, okay, so if this is z equals 0 as I've drawn it here, then whatever this surface is, it touches it at a single point, and it never goes below it, because like we said before, it can never have z negative. So whatever it is, I don't know exactly what it looks like, but it has some kind of minimum there, whatever that surface is. Okay, let's keep going then. What about z equal to, say, 1? Well, what does this equation look like? X squared plus y squared equals 1. Well, that's a circle of radius 1 in the xy plane, right? In fact, for different values of z, for positive values of z, clearly x squared plus y squared equals, and you could replace this with anything, 2 or 3 or 4. Those all describe circles of radii that are getting bigger and bigger and bigger. So if you look at these z slices, let me erase what I have here. We don't actually know that's what it looks like yet. We know that it intersects z equals 0 plane at a point. It never goes below that plane. And if you look at higher and higher intersections of it, or that is to say, higher and higher slices, horizontal slices of it, they're just circles that keep getting bigger and bigger and bigger. All right, so now we have this idea of what's happening with horizontal slices. What about other slices? What about slices like, let's say, I'll jump to a different color here. What about slices where y is constant? Or where x is constant? If x is constant, if we say, look, what about x equals 0? Plug that into the equation. That would be the same, by the way, not taking horizontal slices now, but these x constant slices, they look like this. So these are slices that are kind of coming out of the page. And now that it occurs to me, because I'm going to draw it, I don't want to do that. I want to maybe look at these y constant slices where they're kind of off at this off angle. So it doesn't matter, there's a certain kind of symmetry here. But let's look at y equals 0. If I plug y equals 0 into this formula, what am I going to get? X squared plus 0 equals z. Well, that's just a parabola in the xz plane. So this y equals 0 is kind of this plane right here, and this is saying that we just get a parabola right there. And what happens if I change y to 1 instead? Then it's x squared plus 1 equals z, which is the parabola shifted up by 1. If I pick y equal to negative 1, well, again, because I'm squaring it, it still squares to positive 1. So then you still get a parabola up there. So you're getting these parabolas going from this way, that way, and you're getting circles going this way, going down, up. So this is a horrible looking picture, but let's see hopefully a better picture of what I'm trying to show you in Microsoft Mathematics. All right, so here we have those two circles. Let me zoom in on this. There's that little gray circle and that big blue circle. Those are different z cuts of it. And then we have two kind of parabolas here. And you can just kind of imagine what this is going to look like. You want to imagine these parabolas getting higher and higher and higher and higher and higher. Unfortunately, Microsoft Mathematics only seems to allow me to draw 4 things at a time. But really, I'd like to draw lots of little circles in between and parabolas all along the way. And so it's a little hard to visualize. You take some practice, but hopefully you can convince yourselves that when it's all said and done, the shape that's being described looks like that. So it has these circular cuts that are horizontal, and if you slice it in either the x equal constant direction or the y equal constant direction, you're going to get something that looks like a parabola either way. So that's how you can kind of figure out what these shapes look like just by picking the equation. You just look at the slices where x is various constants, where y are various constants, where z are various constants. In this case, you can see that the x and the y are pretty darn interchangeable. There's a certain symmetry there. So that's why I only really did it for the y equal constant slices. But let's look at another simple example here. Let's look at the cone, x squared plus y squared equals z squared, except we didn't know that it was a cone. Let's look at some slices here. So we'll ignore this little thing here to the side for now, and we'll just look at the equation x squared plus y squared equals z squared, and we'll look at some slices there. Okay, so let's start by looking at horizontal slices. What does this all look like when z equals 0? Well, you just plug in 0 here. Remember, z equals 0 is that xy plane. We're looking at a horizontal slice. What does this surface, this mystery surface, look like? Well, you plug in 0, x squared plus y squared equals 0. I've said it a million times by now, I feel. But that's just the origin. So it's going to intersect that at just a point. Let's raise the stakes a little. Literally. We're going to move z up, that z equal 1 plane now. So that's z equal 1. That was our original z equals 0 where we just hit it at a point. When z equals 1, plugging 1 into this equation gives us x squared plus y squared equals 1, which is a circle of unit radius. So that point has become a circle. And it's clear that as we increase z, we're just increasing the radius. So we're going to get bigger and bigger and bigger circles. What if we make z negative, like z equal to negative 1? Well, the fact that we're squaring it means that the negative doesn't really matter. Negative 1 squared is the same as 1 squared. They both give you 1. So again, what's happening going up is the same as what's happening going down. So you're going to get these kind of circular cuts in this direction. Now the way I've drawn it, I've really made it seem kind of linear, right? But how do I know that it doesn't curve more? I mean, for instance, consider the following. I'll try and do my best. Consider the following curved surface. Looks more like an hourglass. Well, these all have circular horizontal cuts, don't they? And yet, if you kind of look at their other cuts, it would look more like this. It kind of look like two parabolas kissing each other. Not like a cone. A cone, the way I've drawn it, if I take some kind of cut like that, it looks more like that. Actually, it looks like this picture I've drawn already over there, right? So the moral I'm trying to get across here is that just because you know, let me erase some of this other stuff here. Just because you know that it's built up out of these horizontal circles, just because you know what the horizontal slices are, that doesn't necessarily mean you know what the shape itself looks like. Okay, I mean, even the sphere, consider the sphere again. The sphere, all of its horizontal slices were also circles, and yet it looks very different than this. So it's really not enough to just look at the horizontal slices, the z equal constant slices. You gotta look at some of the other ones. So let's look at x equals 0. What does that look like? If I plug in x equals 0 into this equation, we get y squared equals z squared. So keep in mind, x equals 0 is this plane right here that's parallel to the screen. Okay. Now the reason I've drawn this picture over here is because you might not remember what y squared equals z squared actually looks like as a graph. So I've reminded you here on the xy plane what these sorts of things look like. X squared equals y squared is actually the same as saying x is equal to y or x is equal to negative y, because when you square it, you'd get rid of the negative. In either case, both of these equations would imply x squared plus x squared was equal to y squared. So when we have the equation x squared equal to y squared, as tempting as it is to just take the square root of both sides and say it's x equal y, it's the same thing, you actually have to say it's x equals plus or minus y. Those give you two different lines, and they give you this kind of this cross shape just like that. Okay? So let's go back to this. When I took the x equals 0 slice, we got the equation y squared equals z squared. Okay? So that must look like this. So that's how you know that it's not, like two parabolas kissing, or it's not a circle or anything like that. You look at this slice, the x equals 0 slice. This is a little bit harder. Let me go back to the things I've already drawn. I'm going to use them right here. This x equals 0 slice, I'm going to kind of draw an x-ray picture of it, because you can't see it behind this x equals 1. The x-ray picture, it's just this nice kind of straight up cross like that. Okay. Now what if I made x equal 1? Well, if you plug that into this equation, you get 1 squared is 1 plus y squared equals z squared. Or, if you like, you can rewrite that as z squared minus y squared equals 1. All I did is I subtracted y squared from both sides. Some of you might realize this is a hyperbola. Okay, so you look at these kind of cuts and you get these hyperbolas in place. So I'll kind of try and draw this for you. The picture should look like this cone. Okay, so clearly all the horizontal slices are circles, and if you look at this main slice down the diameter of the top circle and the diameter of the bottom circle, then it's going to look like this cross here. But if you imagine another slice that's not quite hitting the circles in their diameters, it's going to slice it like this. It's going to come back down like these, and then it's also going to slice it like that, and it's going to come up like this. And that shape that you're seeing there, if I graph it, it looks something like this, and that's a hyperbola. Okay, so an equation like this, of course this is one that you guys hopefully should already know by now, but an equation like this gives a hyperbola in these YZ plane, or the YZ cuts of these things. Okay, so you have these hyperbolas that kind of get bigger and bigger and bigger. And if I draw this, remember that I drew a similar picture for the sphere. I looked at the different horizontal slices and I showed them all as if they were on the same plane. If I draw these x equal constant, or for that matter, they could have been y equal constant slices, as we get closer and closer to this diameter, the hyperbolas start getting closer and closer to each other, until eventually what happens to the hyperbolas is they absolutely intersect and kiss at a point, and that's exactly the cross that we had here. So it's very hard to kind of draw this, but that's kind of the mentality that you want to employ here. Hopefully this gives you some idea of the picture of how you can take an equation, look at the slices by setting x equal to certain constants, y equal to certain constants, or z equal to certain constants, and try to piece it together. Here you kind of have a family of hyperbolas that are getting bigger and bigger until they flat out intersect at this perfect angle, and then they kind of get smaller and smaller again. So I'm of course drawing them very far apart, but then you also have these circles that are horizontal. And I guess what I'm trying to draw here is a very wide-looking cone for some reason. So it's not meant to look that wide, but hopefully you can see that it really does describe a cone, as you can imagine. So the moral is look at slices. So hopefully I'll make some more videos where we'll look at things like hyperboloids. Maybe we'll review this idea of this equation being a hyperbola more precisely. And then we'll look at other interesting surfaces. You know, they don't always have to have ellipses and parabolas and hyperbolas in them. They could be a lot more interesting. And we'll see examples of that later.